So I started my timer. I have no need to get through anything. I spent my summer reading The Magic Mountain, and somewhere about 300 pages in, like being lost in craziness, there's this quote, which I didn't recover for like 5 days. I think you've all read it by now. Between life and inanimate nature, however, was a yawning abyss, which research sought in vain to bridge. People endeavored to close that abyss with theories. It swallowed them whole, and it was still not an inch less broad or deep. And I felt like 100 years later, Thomas Mann was just stabbing a knife into my back, but the book is amazing. It's written in the Weimar in the 1920s, seems somehow surprisingly relevant today, the angst of the whole thing. But it's a good way to waste a summer. Anyway, I'm going to tell you about some stuff. Well, Vincenzo said he was still digesting the food. Right now, I'm going to tell you about some stuff where me and Yanni are still eating the food. And we just thought, we'd have some dinner conversation while we're eating. So it's not well formulated. It's some very speculative ideas. But I think we showed it to two of the biologists we respect the most, Andrew Murray and Julie Theriault, and they both found it very interesting from a biological point of view. And I'm pretty convinced it's pretty interesting from a mathematical point of view. So here's some half-chewed food for you. So here's the thing that always bothers me. It's going to be all on the board. I just wanted to show this picture because I find pictures like this very, there's a visual element to this, an aesthetic element that you can't convey with just words, which is like, anyone want to guess what the function of this hairball is?
To impress.
Okay, what the presumed function thing of this hairball is? This is the simplified core hairball.
To confuse biologists.
No, it's a circadian oscillator. Okay, it's an oscillator, right? So it's an oscillator. It's an oscillator. It's a very well worked out oscillator. It's the mammalian circadian oscillator, and there'll be things that you can't see, but there's a gene called clock, right? That's how you know it's an oscillator. You look at the hairball and you're like, there's something called clock, so it must be a clock, right? And I think we like to make fun of them, but I actually think there's really an element of truth in all this stuff, which is that if I take some of these genes and I knock most of them out, just take away this degree of freedom, just set it to 0. The thing still works. I take away that one, it still works. I take away 4 of them. Maybe I shift the period a little, or maybe it doesn't quite bifurcate, but it all works. But when we think about it in our models, or this is the famous synthetic biology repressilator of Michael Elowitz, what we draw is something like this. I have one protein that negatively regulates another protein that regulates another protein that regulates another protein with 3 degrees of freedom. And if I knock out one of these or make any mutation, everything breaks loose. And in fact, these are very unrobust. If you know this literature, the last 20 years have been spent trying to figure out how to make this thing actually oscillate for more than like 3 lifetimes. And I would argue that what's interesting is there's something fundamentally missing in our theoretical conception, because we like to write this because we can understand this. Real biology, certainly every arrow can't matter, but why do our math models look like, this when the biology looks like this? So what I'm going to try to tell you is what we've been thinking about is,
since we're in Chicago with Mike Rust, in the bacteria, it really 3 proteins works, and so on.
It is the exception rather than the rule, right? So what happens is in biology, we find these places where we can take away the hairball. So we'll come back to this question. The question is, can we have a model that interpolates between this and that hairball?
Is 3 the minimum just because of...
3 is the minimum unless I put a time delay.
Yeah.
Actually, indeed, wasn't there... I had this vague impression that Jim Collins or something took the repressilator and mildly modified it.
Nama Barkaya.
Oh, okay.
Yeah, you make it a relaxation oscillator, it works very well.
It works really well, actually.
Yeah, and Johan Paulsen, if we want to get into the thing, Johan did it recently, and it was like a degradation tag. If you change the degradation tag, it works really well. It's still a relative statement, but yes, much better than the original Elowitz oscillator. All right, so that's all the slides that I really wanted to show for now, and now we're going to go to the board. It's just a visual thing, right? There's a qualitative difference between this and that is all I want to make.
For sure.
Right? All right.
I'm sorry, you want a model that expands or you want a model that contracts? Or you want both?
I want to understand what the relationship. So let me try to write what's going on. It's a great question. So I think here is what I think defines these biological networks axiomatically, and I'm going to build you a model. It's a forward construction. It's basically, how do I hide? You know, what I would say is that somewhere in this hairball is hidden this low dynamical system. But I think what's going on is that, you know, I would say these networks, what defines these hairballs is that they're kind of over parameterized in the same sense, in some sense that I think Chicago has been doing, which is that I can knock out degrees of freedom. Like literally, I take the gene, I knock it out, I turn off a neuron. The thing still makes the same thing. They're kind of, you know, over parameterized / robust / what Eve Martin, like, what does Eve like to call this? Oh, she has a different word. She doesn't like the word robust.
I mean,
Yeah.
are you meaning that, if I look at this limit cycle, it's like there's negative maximal Lyapunov exponent, things like that. I mean, if I want to quantify it,
Yeah.
if I just perturb it a bit, I go back to the limit cycle for small perturbation.
Yeah, but that's changing the actual expression. When I'm talking about it, I structurally just cut that out. I'd say I project my 5-dimensional thing and I take one of my variables. I have some dxi dt, right? I have some vector of equations. Whatever, dx dt equals some f of x. And I just clamp all x, whatever, 4 to 0. I just plug it in. And I start doing that over and over again with different things. Right? The behavior is basically the same. Yeah.
So you're pruning nodes. You're
I'm
not
pruning nodes.
edges.
Yeah, pruning nodes. I can also prune edges. That's also fine. They're both fine. I can prune edges also. So if I write this as a big expansion of something, so here's a particular one we'll do. Here's a big, horrible polynomial. This was supposed to come at the end, but it's a big, horrible polynomial. You know, it has it's probably like a 1, 2, 3, 4, 4th degree polynomial or 5th degree polynomial with a lot of coefficients. And I can almost certainly set almost all of them to 0, a big fraction of them to 0. These are the questions I would like to know. How many can I set to 0? How much can I change them and still do this? This, like the earlier one, you will be unsurprised to know is an oscillator in disguise. All right. So how do I'm not, what I'm going to tell you is really dumb. On the other hand, me and Johnny have been debating for like 10 months whether this is the dumbest thing or the smartest thing, and we haven't been able to convince ourselves either way. So I just thought, let's make some dinner conversation. You know, we just sit around in coffee shops and do this. That's what we do in Boston. You should join us. It's very fun to be at the coffee shop with me and Johnny. At least I think it's very fun to be at the coffee shop with me and
And what
Johnny.
is R of X?
R of X is this big polynomial on the bottom.
Yeah, but
Yeah, I'll show you. I mean, so the whole thing is this is the construction. So my only point is that you asked about edges. Edges would be the coefficients of, you know, various terms in this polynomial. And I would like to set those to 0 too. Those would be the interactions between genes. All right, that's all right. So they're over parameterized and robust. And the game and the other gambit of this thing is that the actual dynamics is low dimensional. And the actual dynamic variables are actually collective in terms of genes. Right? That somehow what we get wrong in this picture is that we want to always describe the dynamics in terms of genes, but maybe what, right? Who says that biology wants to describe things in terms of genes? Maybe the natural way to describe it is in terms of collections of genes. Right? And in neuroscience, largely due to some pioneering work of many people sitting in the front row and others, right? We know that that it's not the individual neuron that encodes the dynamics. It's really collections of neurons that encode the dynamics, right? And the Hopfield model is probably the canonical version of this, right? And so what I want to show you is that we want to understand, right? Can we make good toy models of hairballs instead of good toy models of synthetic circuits? That's basically the goal. And if we can do that, then it should be modular. It should have this robustness in a deeper sense where I knock out degrees of freedom, I knock out things. And it's going to obviously be, by definition, over-parameterized. So here's a dumb thing. We wrote this little review. I've been thinking about Hopfield models a lot, largely in terms of self-fate. We wrote this review for the annual reviews of biophysics. We have a recent paper where we think about how if instead of just memories, you also give me a bifurcation between memories. How do I build Hopfield models that do that? So we spent a lot of time thinking about this, right? So I give you some attractors. And then in the end, I realized I didn't understand the Hopfield model as usual, like everything until for 20 years. I probably still don't understand it, but I understood one more thing. And when I understood one more thing, I understood how to make these hairballs. So let me tell you this one more thing I understood about the Hopfield model. And in particular, this variant of the Hopfield model that Veronique wasn't in the theorems that were discussed yesterday by Veronique. So here is the thing. So that was the introduction. So I have a little timer. Let me see how much time I have. So I wasted 11 minutes of your time, and you volunteered to give me 29 more. So let's do some more thing. Okay. So here is a funny way to look at the modern Hopfield model, and it's not the one you said. Actually, the Lyapunov function or all that stuff is going to have nothing to do with anything I'm going to do. I'm going to tell you a kind of a geometric way of looking at the Hopfield model, right? And recall, we've had many talks on this by now. The goal of the Hopfield model is I have some memories, right? I have some degrees of freedom. And I want to create dynamics such that these memories are attractors of these degrees of freedom, right? And the basic idea is that we realize there's another space that's fundamental to all this stuff, which is, again, the ends are going to be sprinkled, as Vincenzo said, as needed, but they're mostly left out, right? I'm going to create these overlaps. Squiggle dot X, right? That's what we do.
Sine mu dot X.
Huh?
Sine mu dot X.
Sine mu. Yes. Sorry. And now I'm going to do something. This talk might be over in 10 minutes. We'll see. And now I'm going to do something stupid, which is I'm just going to write down a dumb dynamics for the memories.
You don't want the 1 over n in the overlaps. You don't want them.
Oh, the 1 over n's are sprinkled liberally and forgotten.
You want it to be of order 1.
I want it to be order 1. I want the over mu equals 1 is the normalization. It's like I'm cooking like a white person. I don't need the 1 over n spice and all this stuff.
It wasn't meant to be a suggestion.
No, it's just too hard on the board because the conceptual, I'm just, we don't even have results. Like we do have some scaling with n. So I'll tell you about some stuff about n and p in a second. But this is just a review of the Hopfield model. So the modern Hopfield model, right, the version that we didn't do, basically says this. If I look at the magnetization, if I look at the dynamics not in the degree of freedom space, but in the overlap space, then what I do is I basically write dynamics like this. All right? This is exactly, this is gradient of some function f of m, where f of m or e of m, or I don't know what the notation is, but e of m is equal to whatever, mu plus log e to the beta m mu sum over nu. So this is the relationship between this thing, right? So I just say, look, I define this energy function that we're all obsessed with. I take the gradient of it, and I get this. Right? With a minus sign? I don't know. There's a minus sign. That's wrong. Yeah, man. These have to have opposite sign, and maybe there's a minus sign here, but...
Ben and how's a -1 or both?
Yeah. I really need a few spices. But the idea is this is a gradient of some function, which you can calculate yourself. Right? Now, what is the Hopfield model basically say? The modern Hopfield version, this version that seems to work. It says, look, let me take the beta goes to infinity limit. What's going to happen? Well, what I'm going to do is I'm just going to pick out the term that I have the largest overlap with. That's what this thing does. And so the fixed points are going to be, then I'm going to run to mu equals 1 for whatever I have the largest overlap with, mu whatever alpha. Say I have the largest overlap with alpha. What's going to happen is you just run to that one going to 1 and everything else going to 0. That's just this dynamical system. All right?
So, now M alpha is your initial.
Yeah. Initial. So I start with some x. It has some overlap, highest overlap with all my memories. Whichever one it has the highest overlap with is just going to run to that, and that's it. So that's actually the Hopfield model. So now the problem is that this is in this M space. So all the trickiness is how do I lift it back up to this X space? All right. So I have never seen this written down this way. I'm sure there's other people in the world who might know it. I have not run into them, so I'm not claiming any novelty. I'm just saying I did not know it was this simple. So now let me show you the last problem. So the problem is I gave you some dynamics. So let me just abstract it because we're going to do it to arbitrary. I gave you some dynamics in this collective, in these collective variables. It has some very simple, reasonable dynamics I understand instantaneously. And now I'm going to say, how do I write it in this X space? And this is the genius of Hopfield. He's like, here's some simple dynamics. I'm going to lift them up to some high dimensions. All right. So now what I'm going to do it for the simple case where these are orthogonal. It's very easy, and the geometry is linear, but you'll see that it's very easy to generalize the case where these things are not orthogonal. Things are nonlinear. You can do a manifold. It becomes Riemannian geometry. All the math is, the intuition is, it's very straightforward, though it's probably, I shouldn't say that. It's probably technically very difficult for a physicist, very straightforward to see how this is all how the constructions will generalize. All right, so here's the funny thing about all this stuff. So now let's assume, for simplicity, it's not necessary. You'll see that it's very easy to fix this construction. That epsilon mu, or squiggly, I keep calling it epsilon. It's not epsilon at all. It's a squiggle, and it's an xi, and Aditya's laughing because I've done this for about 5 years in front of him in the board and never done it right. Let's say they're orthonormal. All right. So now what I'd like to say is, look, I can write x, right, as sum over nu, squiggle nu, m nu. Right? There's nothing much to say.
Only if P is larger or equal than N. If P is smaller than N, you don't have enough size to provide the basis for X.
Yeah, so what you're I'm going to define this. Yeah, so the whole idea is, I agree with you. What I'm going to do is I'm going to take my X. So let's think about the geometry. I agree with what you're saying. This is the whole idea. That I'm going to lift this thing up. So I have some X. I have some plane in which the memories live. This is whatever P is less than N. So I can always take my X and divide it into a parallel part plus a perpendicular part. It's just a linear projector. We agree with all this stuff.
Parallel to what?
To the plane, right? So I can take any vector X.
The plane that is
spanned by the memories. Right? And then I can write this as the parallel part. I really have this. So the whole idea is these magnetizations are the coordinate system on this plane, this random plane. And I'm going to have a perpendicular part that is perpendicular to it. And the whole idea is that I replace this with a projector. And that's why you can generalize it in Riemannian. For Riemannian geometry, I can do a local projector, and then it has to change. But that's the basic idea. That I can always decompose this way. Right? So now I can say dx dt equals sum over nu, theta nu, dm nu dt. plus dx perpendicular dt. I haven't done anything. And then I'm just going to substitute this dynamics here into here, and you're done. I have a very complicated dynamical system in terms of x, who, if I projected down to this plane, I would instantaneously see that it has this dynamics. Yeah.
Why can you
X
assume
perpendicular doesn't go to zero.
Huh?
Why should X perpendicular go to zero?
Oh no, I'm making constructions for you. I'm going the opposite way, right? I'm going to say I just want to make a class of hairballs for you.
why can you assume the orthonormality of psi?
Oh, you don't have to. I mean, I just need a projector, right? I just need to replace, this is just a projector. This is a coordinate system on whatever tangent plane I want. Locally, I always have a projector. And I do this. I mean, and then I can choose whatever dynamics I want here, but I still have this hidden dynamical system in these right degrees of freedom because I project down to the right degrees of freedom. And so I can put any dynamics I want here. If I first project down to this plane and look at the dynamics in that plane, I'll see this thing. So the goal is not to build an attractor neural network. This is literally the equations of the Hopfield network where I set this equal to 0. That is the same equations that you get in the modern Hopfield network. If I assume this is 0, this is the last modern Hopfield network that wasn't talked about.
If this hyperplane was curved,
Yes.
then the perpendicular would also be related to the curvature.
Yeah, exactly.
of the plane.
Exactly.
Right,
Yeah, exactly.
Geometry.
There's fun differential geometry we haven't worked out. We've only done the linear case where they're non-orthogonal, but yeah, there's tons of linear, okay.
There is nothing curved here. It's a hyperplane.
In this case, no.
Yeah.
It could be, I think.
It's a
in some of the
hyperplane
gen-
spanned by the size, by the member.
Yeah. Here it is, but you can imagine instead size are the local whatever basis for the tangent plane.
So you will not have dimensionality reduction.
No, but there are systems where it could be curved.
From
Many.
point to point, you could
Yeah,
change
because
the
I'm-
turbine, whatever they
Look,
call.
Confused. I thought the goal of the modern one was to have P being much bigger than N.
Yeah, I'm just
Yeah.
telling you some. Yeah, okay, that's fine.
Then it's the complete basis.
Then
I mean, it's a complete basis. But that happens because this class of functions, even when the zeta is. So what you're going to do now, you see what I'm doing is if I write down the modern, we can talk about the modern. This is not a talk on the modern. This is just to show you inspiration.
You can pull the.
Yeah, I'm going to. So like, let's like the point is, if I look at the model, the thing of the modern network, what you see is that the actual equations are this. Which is just xi. And this is just e to the beta mu sum e to the beta. So it looks like this. Let me write it like this. Right? So you take the dynamics, which were the things I wrote down. I lift them up with these random vectors. And the whole point is that the way they chose these things, even when this is non-degenerate, it's very hard for this dynamics to live in the kernel of that. Because this is positive definite. But generically, it just doesn't live in that, right? Because the whole point is that I have many more memories. So it's not quite the geometry I showed you. That was in p less than n. But p greater than n, the same thing will work. What could go wrong? Well, this could have more fixed points if this dynamical system can somehow find a degeneracy of this thing. It's not a big problem. Yeah.
Okay. Everything was super clear until there, and now when you move on to this board, I missed something. So what's new here is to say now, let's say
No, yeah. So this is just this for the Hopfield model is just literally. I'm just going to define some functions, which is I'm going to just say, let me just call this generically some sigma mu. And now there was a diversion about what the dimensionality of the spaces are. Like why can this is a matrix that is n by p. And what's interesting is, of course, that this can have many more than n in the modern Hopfield, and that's what's surprising. But then if you think about this for a little while, it won't be that surprising for you. I mean, to a physicist level. It's just a weird way of looking at the Hopfield model. All I've done is done like one line of algebra, right, so far. Yeah.
Sorry, it really feels like something that's very understandable. So
Yeah.
I want to understand. There's an equation written on the right, which
Yep.
was dx dt equals stuff.
Yep.
And now there's sort of an equation written on the left, which is dx dt equals stuff, and there's a minus dangling.
Oh no, that shouldn't be there.
Okay, cool. So what's the relationship between the equation on the right?
This is dmdt, right?
Just substitute
I just substituted. This is dmu dt. It's the same equation. I just substituted the right hand side.
the board.
It's under the board.
Okay. But it's changed now that p is
Nothing has changed. I just changed notation on you.
Okay.
Sigma mu is this thing. All right. I'm just writing things in suggestive ways. All right. So now I come back and I say, huh. Well, that's weird. I didn't really use any properties of sigma mu mu. This general lifting should roughly work. It definitely work when this is a subspace of that, when it's a lower dimensional subspace than the high dimensional subspace, right, in the original Hopfield model. So let me replace this by an arbitrary dynamical system. In particular, let's consider, I mean, I'll show you some simulation results. I have 12 minutes, so I think I'll be done in 5, and then we can discuss whether this is interesting or boring. I'm open to this is boring. So I think in fact, I never wanted to talk about it, and Yanni just kept telling me it was interesting. And then Andrew and Julie convinced me it might be interesting. Julie convinced Yanni, and Andrew convinced both of us. So let me write down a dumb equation, right? So I want to build that hairball oscillator. So, in particular, I can just say, imagine I have a two-dimensional, bifurcation. I can never remember how these things go, but here's a normal form for a bifurcation. With 2 collective degrees of freedom. Right? So now mu goes from 1 to 2. I take whatever random vectors I want, and I embed these. Now I want to point out the sparsity of these random vectors controls how gene-centric my description is. If they're completely random, then the collective variables are not localized on gene space at all. If on the other hand, one is 1, 0, 0, 0, 0, then there's a gene identified with that dimension of the dynamics. Right? And so you have this tune where you choose the sparsity of this randomness, and it tells you how collective the hairball is.
So the eyes are labeling the genes.
The eyes are labeling the genes. The mu's are labeling the collective things that are doing these things. And I'm just trying to build it up. So that's the whole game. And now I can ask, yeah.
But you're making this choice of the size to be aligned with some axis a priori. But how are you going to get that from the data?
Oh, that I don't know. I'm just giving you a constructive proof. I'm just trying to build math models that now we can go back and ask backwards.
Okay.
When can you do it? When can you not? And these are the questions. How much does deleting the genes change the bifurcation parameter? How does that scale with the sparsity? How does it scale with that? It's just a model.
Also, you can ask if you can evolve to get the parameters with selecting roughly on the function which the M1 and M2 are doing.
Yes.
See, it's a model for the low
That's
dimension to the high dimension.
Yes.
Not the other way. around.
Okay, so
It's a generative model.
this has been studied mathematically. That's what they're saying. So
Yeah.
there is a way. So indeed, if you take a large dimensional dynamical system, which is the case here. And you could ask yourself, when is it that the low dimensional projection is autonomous? This is what you're saying. Now, the next.
That's not what he's doing.
No. This is abstract. But then the question is, and this projection could be localized or delocalized in terms of the dimension. All that is understood, and applied in other fields. But then the question of how do you find this projection be autonomous, which of course is like a needle in a haystack. The way to do it is dynamical BBP.
Yeah.
This I'm sure happens in this case when it works. If you follow the trajectory of your thing, you look, let's say, at the Hessian or the Gramian, the gradient star, then you see a few eigenvalues, like we saw in the very first talk of this conference, right? You had this Wishart thing with a few, and the projection in this direction is autonomous. And then the next question is exactly the one you're asking, whether these eigenvectors of the dynamical BBP tend to be localized in the initial coordinates or not. And that, of course, that's God willing. Depends on your model.
Yeah.
So there is a general, but of course, doing it's easier to say than to do.
Yeah. I don't know. I make no claims to novelty because I'm not a good systematic reader of the literature. I am a Daniel Fisher acolyte. I just sit around and think about stuff until it seems interesting to me. I'm just telling you this is something we found interesting. I make no claims that no one has thought of this, but I just make claims that I think it's kind of interesting that I can go from something that behaves like this, to something that behaves like that, by just changing the sparsity of these random vectors. And okay, maybe it's not interesting to you. It's fine to me. I don't.
But you could follow on this thing. You could follow the dynamics, maybe.
Yeah, you can. So here,
try to see if you see the spectral transition.
Yeah. We haven't. I told you, we're still eating. We haven't even barely written any simulations. I mean, they look reasonable, right? Okay, I read the abstract and it said, talk about stuff you don't understand, talk about stuff in preparation, so please don't kill me for talking about stuff I don't understand. I mean, that's what I'm doing, right?
If I understand well, in the example you're showing, you don't need to identify the right variable because you know them.
I know them. I've constructed them. But then I want to use toy models to try to ask the kind of questions you're asking. I am not a mathematician. I need synthetic data sets. I need things that look like biology so I can understand how to do theory on them. And I'm just telling you a class of models that I think you can do theory on that looks more like hairballs and looks less like the synthetic oscillator. That's all I'm telling you. That's what I came here to say. And you can find it interesting, you can find it not interesting. I don't really care, right? I find it interesting, I think. I'm not sure, depending on the day. Right? So this is a dynamical system. That's just a 5-dimensional embedding of the 2-dimensional oscillator. Right? All I did was,
Just to see, I understand. The equation that is written over there, right? So psi's are constants. So is that correct? So basically you say that X is some linear combination. I have only 2 variables M, and I construct a bunch of new X's that are just psi times M, and
because psi's are constant, but of course the whole point is that if it's a manifold, then they depend on X themselves, and then you get very interesting, it's a general kind of, I don't know. It's a general thing where you can see what you're doing. You're projecting on a low-dimensional collective manifold, and then you're uplifting up.
Oh wait, okay. So if it can depend on X, then it's not true that I can just pull out.
No, you have to depend weekly. You have to have time scale separation. You can play. Okay, I'm just telling you what I'm thinking about with Yada at a coffee shop. You can find it interesting or not find it interesting. It's fine for me.
So coefficients were obtained by random picking something.
Yeah, the random maps telling you. So now my point is now some philosophy. If I try to go and measure every one of these things, it's hopeless. If I try to knock out every one of these things, depending on how sparse it is or not, I'll find if I knock out genes one at a time, what I'll find is the ones where this is pretty localized, these are localized vectors. Otherwise, I'll never be able to learn any of this stuff. And so you can do simulations, right? You can ask things like, oh, here are all the 5xj's. Since I know the M1s and M2s, I get things. And then I can ask what happens as I, do single knockouts, as I do double knockouts. And you can see these are like really robust. The behavior changes. You can ask how parameters change. You can ask how amplitudes change. You can ask how frequencies change. Bifurcations change. So it's just a class of models that I have not seen in the world that I live in. Let's put it that way. I'm sure they exist in the world. That I find interesting because they have this function of being modular. So now I can, of course, not break it into one subspace, but I could break into many autonomous subspaces where I take orthogonal projectors, and in this direction I do this dynamics, in that direction I do that dynamics. So you get modularity for free. And it's hard to see everything. So it's just a construction of something that to me feels more like biology. And if I want to go back to things that look like this, there's a single parameter that controls it, which is how sparse these random projectors I have. So I can interpolate between things that look like this and things that look like this by changing the sparsity of the basis vectors I got. So I think that's essentially what I wanted to say. Like, to me, it's an interesting. It may be more philosophically interesting than mathematically interesting, but there's also lots of questions, which is that I have properties of these dynamical systems I care about, periods, bifurcations. And the kind of deletions I'm interested in is if I set just biology inspired, if I set all the x5s to 0, I knock out a gene. I set 2 of these variables to 0, I knock out a gene. I knock out some interactions. So I set this coefficient to 0. How robust am I to all these things? And there's going to be certain things you're robust to and certain things you're not. And it's interesting for me to understand these kind of questions. I guess that's all I want to share with you. This is what we've been thinking about. It's incomplete. It might not be interesting. I promise you, I debate whether it's interesting enough or not, but I just felt like a fun, I can't, it's one of these things where I keep wanting to dismiss it, but I can't dismiss it after a year. So I share it with you. Yep.
Pankaj, like what happened to the dynamics of the perpendicular? Here you set them to 0.
I set them to 0, but I can add them. I can hide them.
This thing is invariant, right? Like
Yeah.
you are moving in this kind of whatever.
Yeah, as long as the x perpendicular, right? I put dx perpendicular dt is some 1 minus the projector times some arbitrary function. I can put any perpendicular dynamics I want, right? And it preserves this thing. So it has to have this 1 minus the projector. That's what perpendicular means. But then I can choose any function I want, so I can hide this dynamics even harder, right? And so there's a lot of structure in these things. Apparently they've been thought about. I haven't opened my email, so I don't know.
What about initial conditions, right? Because the initial conditions also need to be compatible, right, with your x's, right? So if x is only the sum of m1 and the other
but I think
of m1, they need to be
I think it's implicit that the initial conditions are going to look weird because it's really the initial conditions in M1 and M2, and you have to map them back to this. Map them back to the whole thing.
The system is defined also for not those initial conditions, and there it could have completely.
Yeah, it could have completely different things. Yeah, so we haven't thought about it at all.
You're perfectly right. In the examples that are known, let's say on the machine learning side, you have things like this, where projections are autonomous in an XOR model, and the projection itself is in dimension 8 or 9, and is a dynamical system where you have a complicated attractor. So depending on where you start in infinite dimension, you could get trapped and then your algorithm doesn't work, or you could with crazy probabilities, and all that can be done. But you have the whole. I mean, depending on your system, everything can happen. But the type of theorem says here is that the orthogonal direction you're saying is just small. Around the manifold, but in this manifold, it could be complicated or not complicated or whatever.
Yeah,
and sometimes this
the local construction.
Orthogonal projection has to do with noise. In some cases. So I would like to make a comment on this.
Yes, please.
I don't know about genes; it's not my field, but I know about neural models, neural network models. So in the models that we analyze, the size, which what you call the size, which are what I call the neural modes, are directions in neural space that are not parallel to any of the axes. They are not neural assemblies that include a few neurons and don't include the rest. They are not sparse. They are orthogonal, and they can be smaller than p or larger than p, but they are, if you look at the loading factors, they have loading factors on all the original axes. They are not sparse. And actually, if you simply take your data and do a PCA on your data, you will see that the only eigenvectors that are sparse are the eigenvectors that correspond to extremely low eigenvalues. All the leading eigenvectors are not sparse. So again, your idea might apply to genes. I haven't played with networks of genes, so I don't know. But I can assure you it does not apply to networks of neurons.
No, but he didn't say that they should be sparse.
Yeah, I didn't say that. I just said
It's whether it's localized.
He said explicitly that he said x4 and x5 equal to 0 because Xi only has x1, x2, and x3 projection.
But he also mentioned that you could have a projection.
yeah. I think the whole thing is that I have a tunable parameter is what I like.
Can I make a comment from the second row?
Not an assumption.
One biological comment. So, I mean, the bacterial ones, the circadian clock there is actually sort of in between because there's sort of an underlying thing with 3 genes, and then there's all extra bits in it which make it work better and so on. And so I think that, to me at least, the sort of bigger question is, can one evolve something to end up with this structure by saying you're selecting on something which is like what it's going to do? Like you start with a switch, select something which has 2 points, and then
I kind of disagree with your basic premise of evolution that you start with simple things. I actually think most of what happens in evolution is that you co-opt a very already complicated machine, and that's why you do this.
I didn't say you start with something simple. No. You start with something which is complicated with lots of things in it, but the function is simpler, like it just being bistable. That was
No, I agree with that.
And
I agree.
and
The
then
evolving thing.
go from that on.
Yeah.
But then I guess just
But that would involve doing something besides sitting at a coffee shop and
Yeah.
wasting time.
But the theory comment, I mean, is the thing from Paul Francois and Eric Sidji and Vincent Hakim of trying to, sort of evolve gene networks that do particular things. And one of the most interesting ones is segmenting Drosophila of something which finds, 7 fixed points, settle up pretty simple, find 7 fixed points, all of them sort of on the boundary of the space. And so I think this is sort of in a similar spirit. You have something which you can't interpret, it's a big mess. And it does something which is, sort of qualitatively like how the biology does it in that case.
But it's interesting.
My time is up, by the way. Yeah.
Comments.
Yes, please. do.
Don't know exactly how to write down it.
And the keys you can put them as you can consider them as a bipartite graph, P times n.
I agree.
And the weights, the edges are the weights.
Yes.
These X's.
Yes, agree.
So there's this thing called universality in random matrix theory and spin
Yes.
classes.
Sure.
Is that you can have a sparse graph as long as it's not too sparse, and then you put it in your system, your Gibbs measure, your free energy, etc. It gives you the same value. So universality will tell you as long as those X's are not too sparse, meaning that in every vertex in your graph has a degree that is.
I understand. I know the theorems. Yeah.
And it's exactly the same behavior. So if you knock out those coefficients, as long as you're not knocking out too many of them, then you would expect.
I mean, the interesting thing is that some of them are in the extensive regime, some of them are not in the extensive regime. That's what makes gene biology interesting, that it's actually not. I think it lives in mesoscopic regimes, and that's what makes it hard. If it was all asymptotic, there are genes I knock out in the cell cycle oscillator, it stops oscillating. That's how they found all those genes, or the period changes, or things like that. So I think the part of the thing is that there's a preferred basis in biology. It's the stuff we can manipulate in the lab that we can knock out and do stuff. And so that's why you're not making basis-free statements. So I don't know how much of the math knows that, but there's preferred basis on, and that's the tension that I'm trying to say. I'm saying, look, it's really a fine dynamical system, but there's a preferred basis. This is the gene I can knock out. This is the interaction I can knock out. I care about that, right? And I don't know what to say. I agree with what you're saying. I mean, that's what the whole construction is based on. That like, no matter what I choose, it'll basically work in the asymptotic regime for sure, right? I don't know. You know my time ran out like 7 minutes ago. That was my clock.
2 more questions? Yeah.
Can I make a related comment? I mean, the way you construct it is you start with some essential dynamics, and then you add a lot of variables that don't really matter, right? And that can't really be the case biologically. I mean, because then these other genes wouldn't be maintained. So presumably what happens in biology is that genes are involved in other functions, and that's why they are there, right? Which
maybe, but why? Who says that we have one gene, one function? No, in fact, the whole premise of the whole group has always been that collective variables.
Sure.
And why collective variables? I agree with you, because there were already lots of big machine and I could co-opt them. And that's how evolution proceeds. So I think we don't disagree.
But I think one has to consider that.
But once you evolve the function, right? Once you evolve the function in a setting where there's already lots of things I can co-opt, then the dynamical degrees of freedom can be collective. There's no reason they have to be genes, individual genes. And that's what basically the gambit of the construction, which may or may not be interesting, it may or may not be right, but at least spurred some discussion, so I don't regret talking about it.
Okay, So let's find